Hi, everyone. Can you hear me? Oh, it's really exciting to give a tech talk from the set of a musical. I'm really excited about that. My name is Jiri Tobisek. I'm a software engineer at Wix. And I'm here to talk about my favorite computer science topic, black magic. Namely, the kind of software magic, obviously, which I have been researching for a couple of years now, and which is called code transpilation and transpilers. And I will focus, of course, on JavaScript and on front-end. Now, I don't know if you noticed, but front-end is full of magical tricks and full of magical thinking. And that's probably part of the reason why I'm so fascinated by it and why I like it so much. There's just something about the front-end developers which keeps them attracted to the magical. Just think about the stuff that we are using every day, like polyfills, or monkey patching, or virtual DOM. There's something magical about all this, right? Like things are working behind the scenes, hidden from the eye in a transparent, mysterious way. Stuff just works without us really understanding how. And transpilers are a bit like that. So we're going to talk about transpilers, about what they are, how they work, and how they are built, what makes them tick. But most of all, we're going to talk about how you can use them and what they can do for you. And the major point that I'm trying to put forward in this talk is that there's a silent revolution going on in our field, in the front-end development. And this revolution has been brought about by the transpilers. And it's changing profoundly the way how we are writing code and how we understand code. But before we start, I just want to ask you, how many of you are writing React applications using the JS6 syntax? Right, that's quite a few. How many of you are using Sass or less? Right, instead of writing the old-fashioned CSS. And I'm pretty sure a lot of you are already today writing your web applications in ECMAScript 6 with all its new funky features, presumably using Babel. And I'm sure that almost everyone here has a minifier in his production pipeline, right? You are all already using transpilers. The transpilers have gone mainstream. They're no longer fringy technology. All the technologies that I just mentioned have code transformation, a transpilation at their very heart. But what exactly do we mean by the word transpiler? Simply put, transpiler is a program which rewrites other programs. And that's why it's sometimes called source-to-source compiler. We have, for example, our CoffeeScript snippet, like in this example. And when we feed it into CoffeeScript transpiler, it gets translated into JavaScript, right? It's the same code. It does, hopefully at least, the same thing. But it has some special property now. It can be, unlike the original CoffeeScript code, it can be actually executed in the browser. What's important about the transpilation is that it's a continuous process. It's circular. It's part of our build pipeline. So we have our bunch of source files, and we feed them through the transpiler. We get our target code, and this target code can then be distributed or shipped into the world. And once we modify some of our source code, we have, of course, to rerun the whole process again and to resynchronize the target code with the source. Now, it's obvious that there is a gap now, right, between the source that we write and the target which is actually executed in the browser. This gap is the very essence of transpilation, but it's also its major weakness. And everyone who tried to debug transpiled code probably knows what I'm talking about. You have this discontinuity between what you write and what you are executing. And part of the attempt to alleviate this problem are source maps. Basically metadata which we generate together with the target code. And this metadata contains all our development tools need in order to map physical placement in the target code to the source code and vice versa. So if our development tools support source maps, they can make this gap virtually transparent. Well, that's nice, but if you think about it, the best thing probably about JavaScript as a programming language is that we can actually run our code directly in the browser. We don't need any intermediate step like in most other programming languages. We can just write our crap directly in the browser and run it, right? And that's awesome. That's what we like about JavaScript. And now, with transpilation, we are basically giving this up. So there must be a really good reason to do that. And I want to go over a couple of such good reasons. As I see it, transpilation is basically a rebellion against the bleak reality of the runtime environments that we as front-end developers have to cope with. And they mark the end of dark era of lowest common factor mentality. Back in 2012, when Wix was developing the first version of its HTML website builder, it was pretty frustrating time to be a JavaScript developer. I remember that we were limited basically to the common base of all the platforms that we were supporting. And don't forget that at that time, this list of platforms, to our great regret, included Internet Explorer 8. And now imagine the same year, Chrome and Firefox were already introducing the first features of what we today know as ECMAScript 6. And you could actually have a sane variable scoping, for example, the same year, using const and let in those browsers. But we couldn't use it. We were stuck with medieval dated JavaScript of Internet Explorer 8. Now, today, the situation is totally different. If I think, as I do, that using the features of ECMAScript 6 makes my source code more beautiful, more readable, more fluent and expressive, and I want to use it because it's just better source code, I don't have to compromise anymore. Transpilers took this problem away from me. So I just transpile my ECMAScript 6 code, and I can run it on all the platforms that I support, even though none of them actually supports all of the features that I'm using. That's great. That's really wonderful. But more than that, I can actually test drive future features of languages. So not only I don't have to wait for specific features of JavaScript to arrive to the runtimes, I can even test them before the spec is actually finalized. And this is great because the community can provide faster feedback. We have much better standardization process like that, right? Actually, the technical committee, TC39, which oversees the codification of ECMAScript, explicitly mentions transpilers as part of this process of creating standards. It's already part of the process. There's an interesting case of CoffeeScript, the widely popular client-side language, which always existed just as a transpiled language. It never had, of course, a dedicated platform, right? But still, there were features like arrow functions, which became very popular in this language. And because of this popularity, because of this community feedback, they made their way into the standard of ECMAScript 6. There's, of course, the case of TypeScript, which lets us imagine how would JavaScript look like if it actually had a type system, a real type system and type annotations. So that's great, right? But we can go beyond that. We can actually code in languages which were never meant for browsers at all. There has been a sense in the JavaScript community for some time already that JavaScript can be a bytecode or assembly code of the web. That compilers can actually target JavaScript the same way they target JVM or assembly code. And there is a feeling that we can maybe replicate the success of JVM as a host for non-Java languages, that we can replicate the same thing with JavaScript. And it's probably not by chance that actually the most successful projects, in my view, in this category are actually ClojureScript and Scala.js, two JVM languages. But more than that, you can even design your own language and write a custom transpiler for it. You may realize that some sort of problems that you're dealing with can be actually solved better if you describe them in a grammar which is tailored for them. And such example of a domain-specific language, or DSL, would be JS6. When Facebook came up with React, they showed this new way how you can actually describe the shadow DOM of a component. There was a big excitement, I guess, about this new way. Basically, a shadow DOM in React is just a functional expression. It's a pure code, and that's very appealing. But on the other hand, as you can see, it's far from comfortable. It's far from easily readable. It's not such a great format to work with. So since the very beginning, Facebook included in React this JS6 language, this language based loosely on XML and HTML, designed specifically to describe well shadow DOM of React. And on the other hand, translating very easily to JavaScript in a very straightforward way, as you can see here. So since the very beginning, since the first public version of React, there was a JS6 transpiler, a custom transpiler transforming JS6 files to JS. And once you realize that you can actually write your own custom transpiler, that it's not that far-fetched to do that, suddenly the whole new world opens in front of you. You realize that by stretching this very idea of transpilation, you can actually do a lot of interesting things. So this is the first demo that I want to show you. So let's imagine we have a platform. And this platform is running some kind of third-party, untrusted user code, like plugins, for example. And because it's JavaScript, and JavaScript is notoriously not very secure language, we want some kind of control over what's going on in this user code. We want to sandbox it. We want to know what kind of values are being passed between all kinds of internals of the code, and maybe prevent some of them. So it can be, for example, access to the global scope that we want to prevent, or access to the internal code of our platform, or just passing around secrets like SSL keys, all kinds of stuff. Now, For the sake of simplicity, I decided to implement a sandbox which prevents the user code from passing around values which contain 4 little f words. So here we have our playground. There are some variables which contain strings like flame, flippers, fairy. And you can see that everything is running without any problem. We don't have any offensive 4 little f word here. Let's try to introduce some. So, Fury. And you can see that our sandbox threw exception because it encountered a 4 little f word in one of the values. Now, you may say that this is a pretty trivial example, and you can solve this actually very easily just by scanning the source code, just looking for regular expression match. That's not a big deal, right? So let's try something more complicated. We have a code which has a function f, which takes a word as a parameter, and it puts f in front of this word. And we have an array of words like lame, lippers, and early. And we're mapping all those words through our f function. And we're getting flame, flippers, fairy, against no offensive word here. So let's try to change some. For example, to delete elf from flame. And again, the sandbox caught the offensive 4 little f word fame and threw exception. And you can notice that the word fame doesn't appear at all in the source code, right? It's totally dynamic value. So how did we manage to catch it? The magic is, of course, in transpilation. We are constantly transpiling the user's source code into slightly modified version. We are just going over every expression, and we're wrapping it in a validate function. And this validate function, in our example, just checks if the value is string, it applies a regular expression and detects 4 little f word. And such sandbox is pretty hard to break, actually. It's actually a pretty powerful technique. What I wanted to show in this first demo is that you can use transpilation not only as a normal build tool, you can use it as a programming technique. You can use it as a strategy in order to achieve results which are sometimes difficult to achieve by other means. Let's say I managed to make you a bit more curious about transpilation. So let's write our own custom transpiler. For that, we of course need to know how such transpiler works. How do transpilers out there in our ecosystem, how do they work? So it's pretty clear that I can't just scan the source code as a plain text, right? I need some deeper insight how the source code is structured. I need the abstract syntax tree, so-called AST. AST is a nested structure, nested data structure, which describes every single meaningful point in our source code. So every node in this tree corresponds to some part in the JavaScript function declaration that I'm showing you in this example. So we have all kinds of nodes. We have identifiers. We have block statements, call expressions. There's tens of types of nodes inside our abstract syntax tree. And of course, abstract syntax tree is produced by a parser. And there's a couple of interesting parsers in our JavaScript ecosystem. These parsers are parsers of the JavaScript language written in the JavaScript language. So the most veteran and most well-known is Esprima, and followed by Acorn. But there's an interesting parser, part of the Babel package, Babel being the uber popular transpiler for ECMAScript. Babylon is probably most modern of them, and I recommend using it. It's a great parser. There's also an interesting project called JSON. When you're designing your own domain-specific language, for example, you may want to actually describe your grammar as a declarative data and let JSON to create the parser for you. You don't have to go through the whole development of the parser. This is what Jeremy Ashkenaz, the author of CoffeeScript, this is what he did. He created the CoffeeScript parser with JSON. So it's worth checking out this project. Once we have our AST, we have basically two options what we can do. We can create either a monolithic transpiler or a composite one. Monolithic transpilers are relatively simple. We have the parse phase where we get our AST from the parser, and then we feed it into emitter. Emitter walks this abstract syntax tree, it traverses all the nodes, and writes out sequentially the transpiled code. The whole magic of code translation is happening in this process of sequential write-out. And that means that this part of the code is composed of many interdependent parts. The whole emitter is basically a monolith. It's very difficult to get into it. It's very difficult to extend from the outside such program. But on the other hand, it's very efficient, and it's a very fast method. And if you have a system which is by definition closed, which is tightly designed, this is probably the method you want to use. And this is what CoffeeScript transpiler does. And this is what TypeScript does, and CoffeeScript. But from our point of view, in our context, more interesting method is the method of composite transpilation. So we have now three phases. We have a parsing, which creates our abstract syntax tree. And then we transform it. We create a modified version of the original AST. And this modified version, we feed into a program called generator. You can imagine generator as basically a reverse parser. It does the same job, just the other way around. So it takes AST and writes out a source code. And theoretically, if we did no change in our transform phase, our generator would produce the original source that we fed into the transpiler at the beginning. What is interesting about this method is that you can actually compose the transform phase out of many reusable small parts, which are independent one from each other, which are decoupled. And so in a natural way, it produces open architecture. Such transpilers are very easy to be extended. Even more so, they can be actually built as a generic transpilers. You might have heard about those two projects, right? So Recast is the most veteran in this category. And of course, you heard about Babel, but Babel, since version 6, basically works like this composite transpiler. It's an empty shell of a parser and generator, and all the language features that the transpiler supports are external dependencies that you have to supply, that you have to import. And so you can create your own mix of features. You can even mix inside your own transformations. This is really cool, right? This is what we probably want if we want to write now our own custom transpiler. The transformations are traditionally expressed in a visitor pattern. So simply speaking, a visitor has two parts. It has some kind of selector, something which declares what type of nodes we are interested in, and we want to transform. And the second part of a visitor is the actual visit function, which gets this original node and performs the actual transformation. And you can stack up visitors one on top of each other. Mostly you can even run them in parallel, independently from each other. And you can also nest them. So you can create a visitor which in its visit function actually runs other visitors on its subtree. This is an example of a Babel 6 visitor. This is actually the visitor that I'm using in the first demo that I showed you, where we have the selector. We are saying here, please bring on every node which is somehow an expression in JavaScript, pass this node to my visit function. And I'm getting this node wrapped in something which is in the lingo of Babel called path. So I get this path object, which lets me perform transformations on the original node. In our example, we want to replace it. We want to replace the original expression with another expression, with a core expression to a validate function, and pass the original node as a parameter. And we are using a builder. We are using a builder included in Babel called Babel types. So this builder lets us create a new subtree in the AST, which may or may not contain some of the original AST. I want to show you another demo, in which also is based on Babel visitors. So again, we have a playground. There's nothing really special about this playground. It's just the Ace code editor, which you probably know from GitHub. There is a stage on which I have a button. And my user code that you can see here just attaches some kind of handler on this button, listens to the click event, and performs some fairly arbitrary business logic as part of the handling. Now, let's see what happens if I push the button. The code seems to be magically track itself. You can actually see which line is being executed. How are we doing this? So you can guess transpilers are somehow involved, right? If you look at the target code, you can see that our transpiler takes every single statement in the user code and inserts in front of it an instruction, a function call, which dispatches a message telling to whoever may listen to it which physical portion of the source is just about to be executed. So in our case, it's just a line number, but you can, of course, be more precise, more specific to put there the exact offset and end position of the code that is just about to be executed. And of course, in our demo, I slowed the whole process down. So it's, of course, not a real time. I'm delaying a bit the messages so you can follow the actual code tracking, because otherwise you wouldn't be able to see it, right? This was a simple example, although it can be pretty useful, for example, in a web IDE. But this basic, simple idea can be taken much further. You can create a very sophisticated logging system, which creates your own stack trace, follows internal values, which otherwise would be hard to reach. But you can do more. You can have fun with async and synchronous code. So you can turn, for example, a synchronous user code into a set of asynchronous callbacks. And then you can actually take over the control of the program flow. So you can stop the program in the middle. You can pause it. You can basically simulate a breakpoint, or you can simulate a debugger stepping. You can even simulate fake multi-threaded environment in otherwise notoriously single-threaded JavaScript. There's a lot of stuff that you can do with this kind of technique. So I just want to sum things up a bit. Transpilers are here. They are no longer fringy. They have become a fixed part of our front-end landscape. And so you should use them. You should embrace them, because they can bring you a great value. And you can, of course, see them just as an ordinary part of the build process. Just another tool to bring your code. But what I wanted to do in this talk is to encourage you to start thinking in a more creative way about what you can do with transpilers, how you can use them as actually a technique in order to achieve all kinds of goals. And so go and dive deep into this magical world and surprising world of code transpilation. If I manage to get you interested, you can go to the GitHub to see both demos, to see how to write simple Babel visitors. You should certainly check out the Babel package, the Babel program, a very popular transpiler, which has great documentation. So, and also the plugin creation is well documented there. And you can also check out this library, which has been released by the team I'm working in at Wix, called Teaspoon, which lets you write your visitors over TypeScript. So you can modify actually the way how TypeScript produces the target code. You can even modify the way how the type checker of TypeScript behaves. You can model your own type systems, your own type features on top of TypeScript. So thank you very much.